Okay, this is a continuation of the problem that we were working on a few moments ago. I inadvertently pressed the stop button rather than the pause, so we're going to have two segments here. And what I failed to mention in part B was I found a typo in your packet. The number of moles of HCl and KOH that are added should be 0.0600, not 0.600. If we had that amount, we would have destroyed our buffer, which is actually what we'll look at in part D. So now we're just going to take a look at what happens to the pH when I add hydroxide ion to this system. Okay, we've got a strong base, which will 100% ionize or dissociate, actually, and will be neutralized by the weak acid. So again, we're going to need that ice table, and we need to determine our equilibrium concentrations of our weak acid and its conjugate base. Again, we know the original or the initial concentrations. We know how much hydrogen ion is going to get added, and hydroxide ion that will be added and neutralized by the weak acid. So we're going to use up 0.0600 moles of weak acid, and we're going to make 0.0600 moles of acetate. So our equilibrium concentrations here are 0.340 and 0.560, which we will then just plug into our Henderson-Hasselbalch again and determine our new pH, or the pH of that buffer system, and that is 4.96. So the original pH of that buffer system was 4.84. So we've added hydroxide ion, which was neutralized by the weak acid. So we actually have increased the pH a little bit because we've made more conjugate base. And the final part of this problem is what happens, and this is a calculation I'm not going to hold you responsible for, but I want you to know what happens when a buffer is destroyed. Because as we know, buffers have a capacity. If you go over the capacity of that buffer, it's going to be destroyed. So in D, we're going to calculate the pH of this buffer after we add 0.400 moles of hydroxide ion in the form of potassium hydroxide. So we'll look at our ice table again. I'm sorry, that's not a 2. That's a 2. Sorry about that. And we have 0.400 molar weak acid, 0.500 molar conjugate base. And when we add 0.400 moles to that liter of solution, we are going to use up all of that weak acid. All of it is required to neutralize that hydroxide ion. So we have 0 acid left. So we no longer have a buffer system. And we have 0.900 molar acetate. So what essentially we have here is a new problem. And in order to calculate the pH, we are going to need the case of B for acetate. Okay. So the new problem is C2H3O2 minus, it will react with water, reform some of the weak acid, and release hydroxide ion. So this is going to be a basic solution now. No longer a buffer, but a basic solution. So how do we calculate this? We're going to use that ice table again, or determine what that is. Well, we have a new solution. If we can use it as a buffer, it's going to buffer at a basic pH. So let's find out what our concentrations are. We have 0.900 initially molar acetate. We have 0 weak acid, 0 hydroxide ion. Some of this is going to react with water to produce these two. And so we're going to subtract whatever that amount is in the form of X. And we'll add X's here for whatever that change is. So this will be 0.900 minus X. Equilibrium concentration for these two is X. Now, we're going to assume that X is so small that it approximately equals 0.900. Okay. And I'm sorry, I gotta flip this out of the way. And so I've looked up the case of B for acetate, and it is 5.6 times 10 to the negative 10. Okay. And the equilibrium here will be the weak acid, the hydroxide ion, over the acetate concentration. Okay? So, case of B, didn't need to rewrite that. So each of these variables we gave X to. We know this concentration. So what we end up having is X squared over 0.900. We're going to solve for X. X squared equals 5.04 times 10 to the negative 10. X then equals 2.25 times 10 to the negative 5. And this equals hydroxide ion concentration. Remember, we're trying to find pH here. There's a couple ways that you can approach this. You can either calculate pOH and subtract pOH from 14, or you can calculate hydrogen ion using the case of W, which is 1.0 times 10 to the minus 14, and that equals the concentration of hydrogen ion times the concentration of hydroxide ion, and this is the way I did it. Again, or calc pOH and subtract from 14. And that would be done just the same way you would calculate pH, negative log of the hydroxide ion concentration. We know we calculated hydroxide ion concentration. So we know that, so all we have to do is solve for hydrogen ion, and that is by dividing 1.0 times 10 to the minus 14 by the hydroxide ion concentration, 2.25 times 10 to the minus 5. Hydrogen ion concentration, push this up a little bit, equals 4.44 times 10 to the negative 10. And pH equals negative log of that concentration. And our pH equals 9.35. So that's a drastic change in the pH of that solution because we destroyed the buffer. The original buffer had a pH of less than 5, and now we have a solution that has a pH, or a basic pH of 9.35. So the last problem in this this part of the packet is creating a buffer by partial neutralization of a weak acid. And we're supposed to calculate the pH of this buffer system. So we know that we are starting with acetic acid, which its equilibrium equation is such. And the partial neutralization is going to be of this acid, so we're going to be adding base. And our initial concentration of that acid is 0.900. We have 0 hydrogen ion and we have 0 acetate ion. Okay. We are adding 0.500 moles of hydroxide ion, which will be neutralized by that weak acid, so we will be adding or increasing, or producing, I should say, hydrogen ion and acetate ion. So we just need to calculate our equilibrium concentrations and plug that into the Henderson-Hasselbalch equation. pKa of acetic acid and we have a pH of 4.84. Okay, that's it for buffer solution problems. I recommend, again, if you're not following this well or having trouble, do some of those practice problems and we will talk about them or work on them if you're having that trouble on Wednesday this week.